Einstein did, of course, in the last years of his life, did quite a lot of work on old-fashioned, non-linear unified field series, the kind that me and Hilbert had worked on way back in before 1915. Sachs had published a number of papers on a non-linear spinor field theory, in which quantum theory emerged as the weak coupling limit of that theory. And that's quite unlike your idea of
most
attractors, but that there were some. They were very much non-mainstream, but they were in the air around that time in the early 80s.
But that didn't influence
a non-linear theory which would just produce a steady state or a limit cycle or anything like that is kind of uninteresting and not relevant to this. It's the fact that you can generate completely, you can sort of describe all the irregularity of the real world with these low dimension measure zero attractors, and these are the ones where you have this kind of fractal structure to the attractor, and that's the thing which stops you from just arbitrarily perturbing states, because in doing so you
that's what breaks the counterfactual.
That's what breaks the counterfactual.
No, I mean Sachs was certainly not influenced by ideas about the Lorentz attractor or ideas from hydrodynamics and meteorology at all. And I think this is if you're going to try and go down this road, your proposal is a much more realistic and promising way of doing it than what. But I simply cite it because it was an instance of what's always been in the background as a bit of out of the mainstream, but has been an interesting kind of continuing tradition in physics all the way through since Hilbert and me, which is that there have been people who've continued to work on non-linear spinor field theories to try to get out.
There may be some linkage, but as you'll see tomorrow, even from the first slide, I start to use some of the intrinsic kind of Cantor set-like properties of these invariant manifolds.
Can I just
yeah.
It was actually, and it's historical, it was actually Einstein himself that inspired non-linearity, because he was dealing with non-linear equations.
Yes.
And although, and therefore what David and I were doing in our discussions was could we take Einstein's ideas a little bit further and perhaps...
Well, Sachs always claimed that he took it directly from Einstein.
Okay,
he was trying to continue what Einstein was trying to do.
We were independent of Sachs. That's...
Okay, so just to sort of slightly change it.
Now for something completely different.
Yeah, although you see the word this is a talk that I've given in a number of places, but they've always been to. This has always been to a kind of lay audience, not to physicists. So I'll kind of skip over stuff, or you may be just amused by the level of science in this. But on the other hand, there may be a few things you didn't know. Again, I'm not quite sure how. This was a 1 hour lecture, but so what I may do, if I I'll just perhaps, I may not give the whole lecture now. I may sort of again split my talk up tomorrow, because I don't want you to. I know it's late in the day, and people. And if it's me, I'd be getting fed up after about half an hour. So let me just sort of see how I get on, and if I don't quite get to the end, I'll just keep the last bit till the last bit will be actually what the predictions are. I should say this was motivated by. I said this at the Royal Society, which is so there was a BBC programme actually which was based on this lecture, which involved me hitting golf balls on the golf course, and this arose because I said, and this was a lay audience which included the BBC producer who made this programme. I said that this kind of motivation of this talk arose pretty much from a number of golfing partners I've had over the years who said something like, you guys can't even forecast tomorrow's weather right, so why on earth should I believe any of this global warming stuff? Which is kind of fair enough. So, it raised this question, well, how can we be sure about these predictions of global warming and stuff? Now, let me, so we start with this kind of iconic picture of the Earth from the moon, from one of the Apollo space shots back in the 60s. And with an interesting statistic here, that the surface of the Earth is roughly 14 Celsius on average, and the surface of the moon is roughly minus 18, so there's about a 32-degree difference. And when you consider, basically the Earth and the moon are as near as down the same distance from the sun, why is there such a disparity in temperature? And as a clue to answering that question, here's a nice sunny day on the moon, and that was okay. Actually, that's actually, yeah, this wasn't the slide I was going to show. But anyway, this is the last time I gave this talk was at Trinity College, Dublin. Does anyone recognise Trinity College, Dublin? So I tried to find a sunny day in Dublin. This is a challenge. This is a challenge. So I didn't quite succeed. So
you just cheated and put in the background blue sky.
Yeah. But anyway, let's, for the sake of argument, here's a sunny day. Well, it is a relatively sunny day in Dublin. So the question is, what's the difference? Now, well, what's the difference?
Strength of shadow.
Right, so one's blue and one of the sky's blue and the sky there is black. Now, so the sky's blue because there's an atmosphere and photons are being scattered off the air molecules. So the reason one is warm is because there's an atmosphere and the other's cold because there isn't an atmosphere. Now that actually, in a way, doesn't say everything because it turns out about 99%, I think, if I can remember my numbers, of the atmosphere is made up of nitrogen and oxygen. So those two elements, if you like, molecules, make up the vast bulk of the atmosphere. And yet, if those were the only two molecules that the atmosphere was made of, there would actually be virtually no difference between the temperature of the Earth and the temperature of the Moon. So actually 99% of the atmosphere is actually doing nothing to regulate the temperature of the Earth. So what is going on? So here's the next little. I'll bend down here because this is actually a little animation. So here's the Earth seen from actually space. This is a kind of a montage of images from satellites in geostationary orbit, and they show the Earth, or at least they show the atmosphere as a kind of complicated beast. You see weather systems moving from west to east, and there's something going on here in the tropics. Now, what we're actually looking at here is the Earth in the infrared part of the spectrum. So these infrared, what are called infrared radiometers on these satellites, and I remind the audience that infrared is measuring heat, so there's a count in infrared. And I also... Yeah, it's showing this yeah, so also everything, everything releases, everything terrestrial is radiating heat, and including the Earth itself. And so if you go back to this slide here, just animate it once again, what's actually interesting, perhaps, is that we're not seeing the surface of the Earth. We're not seeing the heat really coming from the surface of the Earth. We're seeing infrared radiation coming from something in the atmosphere, because we're clearly seeing this